we will discuss our chapter 8, which is mechanical properties. So dia berkait. Okay, these two chapters is we need to know the mechanical properties of material, which is the experiment, the tensile test experiment. So we can have a look at the table and also the diagram of the stress strain. Okay, so today's objective is understand how to measure the stress and strain. Okay, stress and strain through experiments. So we have some experiments, but it is some kind of examples in this chapter, and a correlate behavior of some engineering materials to the stress strain diagram. Okay, stress strain diagram is coming from the tensile test. For tensile test, we have the specimen, and from the specimen, we give the load given to the specimen. Okay, this is the specimen. Okay, this is the specimen, and this is where we put our specimen here. Okay, that is our specimen, and then load is given. Tensile load is given to our specimen. Oh, slide ni eh. Sekejap eh. Okay. So continue. You tensile test to the specimen is depend on the material. If you want to try the specimen, the specimen, the material. Okay. We have aluminium, calcium, steel, steel. Okay. So it is different on the materials, and then we give the load for the tensile load to the specimen, and we read and we read the elongation. Okay, elongation is strain is equals to delta over L. So the this is we record the elongation, and we get strain because we have the original length. And the diagram is this is stress and this is strain. If you give smaller or equals to P to A, we have the sample study small dengar oh sekarang oke sekarang oke repeat uh, in the stress strain okay stress strain in the uh, stress which is the state specimen. So anything you know about their properties, their stress, pain, their numbers. So it must be the same same um, with diameter 15 millimeter and of 50 mm. That one, very so we know this area, okay, the area of that specimen. So this will mention the area of the specimen, and we can uh, our stress and strain. Elongation record from the uh, machine. Okay, so from this we can get okay, it must be you can change it material. You can draw your graph of uh, um, this is examples of the of uh, stress strain. This is called okay strain gauge. Okay, this is gauge um, tensor most the result is found from the specimen. So known size is the sample. Okay, and then we the force and we elongation. Elasticity, modulus of elasticity of E is a measure of the linear relationship between stress and strain. The Pascal and megapascal is the same unit. The unit is the same. Giga is 10 to the power of mega is 10 to the power of meters in Pascal. Um, Equation of uh, modulus of stress equals to E strain. Okay, ni kita akan tengok dan saya akan explain. This is the application, and this is the stress strain diagram that I um, talk about it so many times for this chapter and for the previous chapter. This is the stress strain diagram, and looking at the y-axis, we have the stress, and look at the stress. Okay. Note the critical status for strength specification, which is proportional limit, elastic limit, yield stress, ultimate stress, fracture stress. So from the stress and strain diagram, let's have a look at this type, okay? This one and this one. Let's look at that one first. So from the stress strain diagram, we have different different region. Okay, different region. Now we look at the first one, the elastic region. Elastic region is like a rubber band. Okay, you give the load, and when you off the load, okay, the rubber band will go to the original place. Okay, so that is the elastic, like rubber band. And then we have inelastic region. It is inelastic behavior. Like I said, if load, it will expand, it will elongate, and if you off the load, if you release the load, it will come back to the original state. Okay, that one. First is the elastic region. Then we have the plastic behavior. Plastic behavior is when we give the load extra from the elastic region, elastic load. Then when we the load, it will not come back to the original place. From that, we know that our material is in plastic region. Okay, in plastic behavior, yield, we have strain hardening and we have necking. So that is the normally we have 4 region in our stress strain diagram. So normally we as an engineers want to our products, our structure not exceeding this one. Okay, that is the best one because when we give the load, it will expand, and we release the load, it will come back to the original. Okay, then we have there a proportional limit. This one, proportional limit. After that limit, it will after what we call behave. Okay, so let's say this one you have elastic region, and then after the proportional limit, it will like that. Okay, and then when you release the load, it will not come back to 0. Okay, so that is plastic uh, proportional limit to the plastic region. Okay. Okay, so this is the proportional limit, elastic limit, yield stress, and ultimate stress, fracture stress, and the maximum, the ultimate tensile stress of our structure, our materials. So again, this is depends on the graph, the diagram is depend on the material. So we have from the figure, we have spring steel, we have hard steel, carbon heat treated machine steel, structural steel, soft steel. So it depends on the material. Okay. Many engineering material exhibit initial linear elastic behavior, where the stress is proportional to strain. Proportional to strain. Okay. When you give the stress, when your stress is bigger, your strain will be bigger. When you increase your stress, your strain will be increased. So that is proportional to strain. And from this one, the proportional state, okay, the proportional state, which is in the first region, elastic, in the elastic region, okay, only in the elastic region we have modulus of elasticity where sigma is equals to E. Modulus of elasticity or Young modulus times strain. Okay, just recap. If we have line and this is y is equals to mx plus c, where c is 0. So we have y is equals to mx. Y is stress, x is strain. Okay, y equals to mx. So m is the modulus of elasticity. The modulus of elasticity is the m in our stress strain diagram. Okay, m is, what is m? M is our slope. Okay, elastic region only. Okay, elastic. The Hooke's law is in elastic region only. Okay. And then we have modulus of resilience. Modulus of resilience is strain energy density, where we calculate our area under the graph. Okay, area under the graph in uh, before plastic region, which is in elastic, still in elastic region. So we can calculate it as 1/2 times sigma plastic times strain plastic. Okay, and then we can change our strain from the Hooke's law from here. Okay, so from here, strain is equals to E. And then we put strain, we get sigma plastic times sigma plastics over E. And that is what we have in here. Okay. And finally, we have modulus of toughness. It measures the area under the stress strain diagram. So this is the area. Okay. This is you need to integrate the equation of uh, our line diagram line. Okay, so calculate the area, that is modulus of toughness. Stress strain diagram, when material is stressed beyond the yield point. Okay, we have this one, yield stress, yield point. Okay, permanent deformation will occur. It will not come back to the original place. In particular, steel has region of yielding whereby the material will exhibit an increase in strain with no increase in stress. So from the graph, we can see that from the elastic region, and then it is past the yield stress, and this is the same value of stress uh, is the same, but the difference is in your strain. So no increase in stress, but increase in strain. Okay, strain hardening region cause further yielding of material with a corresponding increase in stress. So yield material, strain hardening. This is strain hardening. So if you increase your stress, your strain will also increase. But it is not as the in elastic region. Finally, an ultimate stress, a localized region on the specimen begin to constrict, forming a neck. Forming a neck. This is where your specimen will form a neck. Okay, form a neck. Here, ultimate stress. You will have okay, necking. When it start in necking region, okay, so this is necking, you didn't give the load, okay, but it still elongates until it fracture. Okay, so that is the neck, then fracture occurs. Okay, this is how the experiment. Okay, this is sigma equals to P over A to calculate given the load, and it will give you the stress. You can calculate your stress. Strain is the elongation divided by your original length of specimen. Okay, so from this one we have stress and strain. So we draw stress and strain. Data taken from a stress strain test are given in the table. The curve is linear between the origin and the first point. The curve, so it is elastic region. Hooke's law. Plot the diagram and determine the modulus of elasticity and the modulus of resilience. Okay, so you need to plot your graph, strain 224, a strain is 0.016, 234.5, 0.08, so 280, 224, strain is 0.3, 288.4, strain is, so this one. No. Okay, so that is what happened when we run our experiment. Okay, so we draw our stress and strain diagram. So we plot our graph, and then the question is modulus of elasticity. This is sigma is equals to E strain, which is in elastic region. Elastic region is the linear line in the elastic region. Okay, then we calculate our E, and then we calculate our modulus of resilience is the area under the elastic region. So we calculate that one. Okay, that is our stress strain and stress strain diagram, and we know that I have tell you that the parameter that you can change is the material. Okay, you change the materials and you get the different graph of stress strain diagram. Okay, faham eh? But after we have run the experiment, we comes that there are two types of material. The first one is ductile, and the second one is brittle. From the stress strain diagram, it shows a significant, very significant difference between ductile materials and brittle materials. Such as most metals that exhibit elastic and plastic behavior, ductility is usually specified by the permanent elongation to failure or by the percent. So bawah tu tak ada apa-apa. Ductile materials, dia punya stress strain diagram is some kind that we look from the previous stress strain diagram. But brittle material is, we don't have the ultimate tensile stress, so it happened like this. And this is fracture. Suddenly, the brittle material will fracture. Okay, so that is the difference between the graph of the diagram of brittle and ductile material. Exhibit little or no yielding, no yielding. So from the stress strain diagram. Okay, this is the elastic region, and somehow this is actually yield. Okay, the garis rata. No yielding. This is ductile, and this is brittle. The material is like cast iron, concrete, glass as the examples of brittle material. So brittle material, um, no yielding, no yield point, no necking. Suddenly it will fail. Okay, no yield, no necking from the specimen. Okay, stress strain diagram. So from stress strain diagram, we only learned uh, three modulus and one equation. Okay, the equation is from sigma is equals to modulus of elasticity times strain. And then we have learned three types of modulus. Okay, three types of modulus. Modulus of elasticity. Then we have, tak ingat sebab tak banyak, tak selalu pakai. Resilience under the elastic area, modulus of resilience, and also modulus of toughness. Okay, so that's in our stress strain diagram in this chapter. Now we go to Poisson's ratio. Poisson's ratio is about the from the a strain. Okay, from the strain. If we have an examples, if we have uh, a beam and given load P, and we have the what happen if we give the load P, it will act like this. Okay, the elongation of our beam will something will happen to our of beam where we have the elongation. Okay, we have the elongation, and we have also the decrease in diameter. So that is what the Poisson's ratio come from. It will look at the lateral loadings and longitudinal loadings for the strain. So Poisson ratio V is bukan mu. Mu is negative lateral strain divided by longitudinal strain. Okay, lateral strain. Lateral strain is what happened in this one. And along x-axis, this is longitudinal strain. Okay, why it is negative? Because mu is normally positive, but we put it as negative because lateral strain will have a negative value. Sorry, and longitudinal strain will have positive value that will make it a positive one. Okay, negative and negative. So the equation is mu is equal to negative lateral strain divided by longitudinal strain. Let's have a look at the examples. So we have example 3.4, a bar made of A36 steel, okay, has the dimension in the figure. An axial force of P 80 kilonewton is applied to the bar. Determine the change in its length and the change in the dimension from chapter the material have elastically. So the thing that you need here is E, modulus of elasticity, where you can find it from the book at the back of the book, which is mechanical properties. The normal stress in the bar is we have 80 kilonewton, and we have a 0.05 meter times 0.1 meter. Okay, so that's our A, and we get our stress. From the table, we get our E. So this is E steel. You will find that in our question, normally steel, we have 200, 210, 190. So that's the different types of model materials. Okay, and then we can calculate our strain. Stress equals to modulus Young times strain. So strain is equals to stress over modulus of elasticity, and we can get our strain. Then we can calculate the axial elongation. The axial elongation where we have the 1.5 meter times strain is equals to delta over L, and delta is equals to strain times L. Okay, and then we can calculate the elongation. After that, given, what is this? T. ST is, we call it mu. Poisson's ratio of, so Poisson ratio, mu is negative strain of lateral divided by strain longitudinal. Okay, so from that one we can calculate both x and y direction, so we get our answers. Okay, so that is the examples of Poisson's ratio, and this is the another examples of the Poisson ratio. Ada soalan ke? Oh, lag balik buka. Um, sekarang okey tak? Sikit lagi kita nak habis chapter 8 ni. Okay, so ini examples nanti boleh tengok, and finally Okay. Finally, we have from a stress strain diagram, which is normal stress. We have from the normal stress, we have sigma is equals to P over A, and then we have strain is equals to delta over L, and then we get our stress strain diagram. Okay, from the stress strain diagram, we get our modulus of elasticity in elastic region. Okay, so for shear, shear stress strain diagram, this is same like Hooke's law. Okay, so we have tau, tau ni is the same tau. Tau is equals to V over A equals to G modulus shear modulus of elasticity times gamma. So gamma ni untuk kita punya shear lah. Right. So G pun given shear modulus of elasticity, we can calculate and put it in the mechanical properties of our table. Okay. So G modulus, shear modulus of elasticity from modulus of Young and also from the Poisson's ratio. Okay. So ni examples. Determine the modulus of elasticity. So the modulus of elasticity is E, which is Young's modulus. Also determine how much the force caused the diameter of the specimen to contract. So this is shear modulus of elasticity and yield stress sigma y. Okay, so example, and this is examples of the shear, boleh tengok juga, dan itu habis untuk chapter sebab boleh tengok. Sekejap, saya show you. To show you the mechanical properties. The examples of mechanical properties, which is okay. This is the mechanical properties. Table of our mechanical properties. As you can see, Ya Rasulullah. Okay, as you can see, actually up here is okay there. Typical properties of materials in engineering. Okay, so from the figure you can see that look at the first tab. Okay, material density, altitude, strength, yield strength. Strength we have tension, compression, and shear strength. Under yield we have tension and we have also our coefficient of thermalization. So have lot and types of materials that they have. Um, so and aluminium per itu uh, is the of the method. So it's not given real of copper and not copper hand on. What is the yes? Per yang modulus of copper. Ada jawapan. 20. Oh, betul. So look at the uh, time, okay? We look at 450, 50, uh, 60. So from the first material, material is uh, 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 that is second by megapascal. And you need to you use it some as point to be in strength, good resistance of load cost. Okay, so which materials. So strength higher cost. Cost the engineering and you need to find best okay. Cuba tengok. the uh, yes, okay, so I will show you so uh, first one is and then you have yield, and then finally that details uh, yeah, okay for the at the same moment especially this is material uh, for stress and uh, uh, the but if I did trust check trust trust analysis um, okay discuss tutorial ni dalam saya discuss okay discuss and okay and then I also that yang I think tadi another to become
Thank you, sir.
some